All right, this first video is going to be about homogeneity and then how we can write our solutions in vector form. So we say that a system is homogeneous if it can be written in the form ax equals 0. So ax is equal to a b vector that is the 0 vector. Now, if the solution is only 0, for all of your x1, x2, x3s, then we call that the trivial solution, meaning the only thing that really solves this is if everything is 0. If there is a question on whether there is a non-trivial solution, then you can try to figure out if there is a non-zero vector x that satisfies that equation. A homogeneous equation, ax equals 0, has a non-trivial solution if and only if the equation has at least one free variable. So that's really important. I'm going to read that one more time. The homogeneous equation, ax equals 0, will have a non-trivial solution if and only if the equation has at least one free variable. So let's look at an example and kind of dig into this a little bit deeper. Let's go ahead and determine if there is a non-trivial solution, and we'll use that to describe the solution set. So I'm going to set my matrix here. I'm going to augment it with 0. And I can just add the first two rows. And then for my second one, I can multiply row 1 by -2 and add, and when I do, I end up getting this here. And then I can take 3 times row 2, add that to row 3, and we end up getting this as our solution. If we continue to go throughout the reducing process, I'm going to give me some more room here, so I'm going to erase these here. And if I continue to go through the reduction process to get rid of this and put it into reduced row echelon form, we end up getting 1, 0, and -4/3. 0, 1, and 0, and then all zeros. All right, let's remind ourselves what that means. Well, that means that x1 minus 4/3 x3 equals 0, and x2 equals 0. And so my vector for x must end up being, if I add this over, 4/3 x cubed, 0, and I said x cubed, sorry, x3. Well, another way that I can write this is x3 times the vector 4/3, 0, and 1. And so I can actually call this here my non-trivial solution, and it has one free variable here, x3. Now notice this does become a trivial solution if x3 is 0. So that is something to kind of take into account, is like x3 could be 0, and this would become the trivial solution. but as long as x3 is not 0, then our solution vector is some multiple of this vector right here. All right, let's look at another example. A single linear equation can be treated as a simple systems of equations. It's just going to be dependent on our other pieces here. So I could say, I'm going to go ahead and divide everything by 10 so that I have a 1 in the front. So in this case, I'm going to say both x2 and x3 are free, and I know that x1 is equal to 0.3 x2 plus 0.2 x3. And so my x vector, this is x1, x2 is just x2, and x3 is just x3. There should be a decimal there. And so one way that we could write this is x2 times 0.3 or 3/10, either way, 1, 0, plus x3, 0.2, 0, 1. And so just like we called it v before, we might call this vector u and vector v. And then we would know that the vector of x, of our solution vector, lies in the span of u and v because it is a linear combination of u and v. So just to kind of review some of the vocab from our previous lectures and examples that we have done. All right, so it's important to notice that you could write exactly what we have right here in terms of s and t, because x2 and x3 are just real numbers. And so this is just another way that we could write this exact same equation that we had right there. Okay, so s and t are just numbers. This is the same as saying x2. This is the same as saying x3. In example 1, we could have said something like this, or t in r, and that's what then is the parametric vector writing, is if you write it in s and t instead of our x2, x3. It just means that one of the or more of your solutions depend on the other ones, or you have some free variables in there, is what that parametric vector definition is then telling us.